Hello, and welcome back to a look at Arabidopsis. Today's organelle is Tubulin. First, let's take a closer look at our specimen. These are Arabidopsis seeds looked under through a stage microscope. They are placed near a ruler for measurement. They are about a little less than half a millimeter in width. Here we see a time lapse of some of our seeds. Look at them grow. Now here's an image of light microscopy. This was a times image that we'll zoom into, going into a 40 times image and then a 100 times image. From here we'll go into a video of light microscopy streaming in a 40 times image, and then zoom back in to show you a 100 times image of the streaming with enhanced contrast. This is phase contrast, you can tell by the dark side and the light side. This helps bring out contrast of smaller organelles within. Now we'll take a look at phase contrast time-lapse. Here you can see another example of streaming, and I apologize for the darkness of the image. Next we'll move on to a DIC of our root hair. To the left you'll notice the nucleus of the root cell, and on the top you'll notice a tubulin branch anchoring from across the root hair. This could be used as a transport chain, or may it just be a support. Next we'll move into a time lapse of the DIC. Towards the end you'll notice that the branch begins to dissipate. Following this, we'll go into a Z-slice of our DIC. This will allow us to see layer by layer each part of the depth of the root hair. Notice on the left there are fragments of what could be cell remnants, and as we move through the root hair we could see a small example of streaming as well. Once we've turned off the lights, we can see our fluorescence. In these first images we use a dye called calcifluor that dyes the cellulose in the cell walls. This allows us to see its interaction with our organelle tubulin. Here we see tubulin fluorescing on its own because of a modified gene allowing it to fluoresce in blue light. Now we'll take a look at these fluorescent images as they've been processed here to create a 3D image. Here's our finished 3D image colored to help you see its dimensions. Notice how some of the tubulin filaments go vertically up the cell. This is not the norm. Most tubulin filaments will go across the cell, wrapping around in a candy cane type pattern. The structure in the center is just a stem cell. The others on the side are side stem cells that were not fully constructed in the 3D imaging. Here we have more tubulin filaments, and you'll notice off to the right there is some movement of Golgi. Here's another section of filaments with more obvious moving of Golgi bodies. Now let's take a closer look at how tubulin works. Here we have an alpha tubulin and a beta tubulin. These two form a dimer that, when bound to GTP, causes it to join or form a microtubule spiral as seen here. The alphas tend to align to the negative end of the tubule and the betas to the positive end. When the GTP breaks down to the GDP, the dimers tend to fall apart from the tubule. This is how the tubule grows and decomposes to